Okay. It's a pleasure to be here. The title in the program is Repeating FRBs and Future Surveys. I don't know where that S came from. I only know of one repeating FRB so far, but if there are others, I'd love to hear about them.
There's another one that probably not
Right?
It's going to have the same DM.
So the outline of the talk, I'll talk about this repeating FRB that Sarah mentioned, briefly address the question of could all FRBs be repeating, and then talk about future FRB surveys, and I'll emphasize the one that I'm doing a lot of work on, CHIME. So FRB 121102, there's the, we call that the waterfall plot, the frequency versus time plot, where you can see the pulse sweeping through. This was the first non-Parkes FRB. It was found at the Arecibo telescope as part of the P-alpha survey. The dispersion measure was 558, which was about 3 times the maximum according to the Cortez and Lazio model. A couple things to notice about this FRB. Is there a laser? Yeah, just notice it's much brighter at the top of the band and fades out, and that's quite an unusual spectrum. The spectral index, if you just measure it from that plot naively, is about +9. But on the other hand, as Sarah emphasized, we don't know where it is in the beam, and you can have, depending on where it is in the beam, you can get all sorts of different spectral indexes. I'll show you that in a second. In fact, we assumed that that spectral index was due to being offset from the beam. So this is Arecibo, the 300-meter telescope in Puerto Rico. The P-alpha survey that discovered that FRB uses the multi-beam receiver, which you can see down here. It's 7 independent beams on the sky centered at 1.4 gigahertz, each with 300 megahertz of bandwidth. The survey that found this FRB was actually an ongoing galactic plane survey for pulsars and single pulses. So far, the survey has found 164 radio pulsars, including about 13 RRATs. And we've published many papers on this survey, and that's one of the latest ones. In any case, coming back to the repeating FRB, this is the Arecibo beam pattern for the multi-beam receiver, and this here is sort of a spectral index map of if you took a flat spectrum source and you put it in different locations in the beam, what kind of spectra could you get? And the spectra that are down here, the red ones are very negative and gray ones are very positive. And so to get a really strongly positive spectral index, you might think that it has to be in one of those very, very narrow range of phase space in a very precise location in the beam pattern. But of course, and exactly what that probability is you can estimate in different ways. We estimated between 5 and 10%, and that is what we assumed. And then that was detected back in 2012, and we started doing observations to try and search for repeats, although we knew full well that the people at the Parkes telescope who were doing these had not seen any repeats. And so we were kind of gloomy about this endeavor until this graduate student, Paul Schultz, pushed through this data set and found that the source is in fact repeating. This was an effort that was led by Laura Spittler and Jason Hessels. And here you can see that's the original Arecibo detection. And these are now 10 new bursts that were discovered in 2015. 2 in May 2015, 8 in June 2015, 6 of which were within 1 minute of each other. And what you can see by looking at this sort of rogues gallery of all the different waterfall plots, where here the dispersion has been removed, so they've been de-dispersed to the correct dispersion measure, so the lines are all vertical instead of going according to the 1/frequency squared law. You see all sorts of different behaviors. There's some really, really bright ones with very positive spectral indexes, getting brighter to the high end of the band, and then this one compared with this one, which are less than 20 seconds apart. You can see this one is actually really faint at the top end of the band, really bright at the bottom of the band. And similarly, here's another one really bright at the top end of the band. So what you see are great diversity in the spectra and the morphologies also of these repeat bursts. This is a plot that shows the location on the sky of the initial discovery observation made in 2012. That's the multi-beam receiver pattern on the sky. In black was that original observation, and here circled with a number 1 in it, that was the first detection. And then when we were looking for repeats, we tiled the sky. The red beams are the 6 different center beam locations for different pointings that we were trying. And the circled, the solid circles are the locations of all the repeat bursts that we saw. And so you can see, even though we definitely covered this region over here, all of the repeat bursts were found in this local, in this small area of the sky. So what we conclude is that indeed the very first event was actually in the side lobe, even though it seems quite unlikely. Although the fact that the spectra are so incredibly variable says that what the spectrum is doing for that initial one isn't really that interesting. We can't say exactly where it was in the beam still. And so the error region is somewhere inside that 3 arc-minute overlap area. We've now also detected this repeating FRB at a different radio telescope, at the Green Bank radio telescope. This one at S-band at 2 gigahertz, so somewhat higher frequency. We have one detection on one day, and then a few days later, 4 more detections within 20 minutes. And you can see, again, very interesting spectral shapes. In this case, it just nicked the top of our band. We don't see it at all on the bottom of our band. In this case, it's quite bright in the middle of the band, but falls off on either side. As for all of the Arecibo detected bursts, the dispersion measure is, or the dispersion sweep is fully consistent to very high precision with cold plasma dispersion. And also all of the dispersion measures are consistent with a single value. The uncertainties, of course, that we measure for any one particular burst will depend on how broadband it is and on how bright the pulse is. But for the really bright ones, you can measure it very well, and they're all consistent with a single value. Something else that's interesting is some of these bursts are very clearly have widths that are very well resolved, and there's quite a variety of widths, and I guess Sarah showed that. If you compare the distribution of widths of the repeating FRB to those of FRBs in general, you have to be very careful, because the published widths for many of these fast radio bursts are actually not resolved by the instrument. And when you account for that, it looks like the burst widths in the repeating FRB are somewhat wider. It's a little hard to quantify that because of this instrumental effect that I just mentioned. Now you see that sometimes we detect it, sometimes we don't, very hard to predict, but the bursts do seem clustered in time. This is now a plot that shows you all the different observing sessions that we've had of the source. These are all the different telescopes. You can see there Arecibo with the alpha receiver, Arecibo with a different L-band receiver, the Green Bank telescope at Effelsberg, we've looked at it, a whole bunch of different telescopes, lots of observations, but only the circled observations have shown bursts. And in fact, several of them have multiple bursts. And so what we conclude is that they seem clustered in time. It's a little hard to quantify exactly that, something we're thinking about. And I should just mention that very recently, in fact in the past week, we've been on air again looking at it with Arecibo and have detected it several more times. The fact that these bursts are clustered in time hinders our ability to localize it, and there are big efforts to try and do that. We have coordinated VLA, Arecibo, Green Bank Telescope, European VLBI network campaigns, but these campaigns require the source to cooperate, and so far we have not managed to get a burst while looking with the interferometer, but we have observations this week going on until next week, and hopefully the source will be kind to us.
How long was the duration nature of this surface?
Is each of these
Observations, how long?
a few hours. Yeah. Okay, so one question, could these bursts be coming from a galactic source? And this is something that we have thought a lot about, other people have thought a lot about, and the conclusion is it's very hard to understand this as coming from the galaxy. You might think perhaps the excess dispersion could be coming from some sort of local cloud, some sort of H2 region, but there's very severe constraints on what could be doing that from various emission arguments. So, for example, the fact that the spectrum is so hugely variable, changing from being incredibly positive spectral index, negative spectral index, to really no spectral index because it's peaks, it suggests that there's no free optical depth. It's there's no free absorption at all. That's very constraining on the size of the object. That has to be able to contain all of that excess dispersion measure. We see no deviations from the cold plasma dispersion law to very high precision. And in any case, if you were to have, given all of these constraints, and you wanted to have some sort of local cloud, that cloud should be emitting. For example, and I'll mention this is discussed quite at length, and actually is incredibly helpful to have Kulkarni et al. Paper from 2015 discussing our source in particular before it was known that it was repeating. But you would expect continuum-free emission, and we can put very tight constraints on that from VLA observations. You might expect some H-alpha emission. There's absolutely nothing there. There are some ways of getting around some of the different constraints, but because the DM is constant, we can rule out these interesting models that were proposed for the population in general, and I refer you to this paper for details. I'll just show a little bit. This is predicted 1.6 gigahertz continuum emission from assuming no free absorption, basically thermal Bremsstrahlung emission for different types of temperatures. This is the predicted flux that you should get with all the constraints folded in, and the VLA upper limit is way down here. It's very hard to understand, and this is images of the field in continuum radio emission, X-ray emission, 22 microns, H-alpha, and there's no evidence for anything that isn't, that could be the counterpart. I could say this very quickly. The Chandra, we've looked with Chandra in a director's discretionary time observation. There is actually one Chandra source that is in the overlap region. This again that's the 2012 localization region. This is the 2015 localization region. That's the L-wide receiver beam pattern. There is one X-ray source there, but it shows no evidence of variability, and the probability of chance superposition of something totally unrelated is fairly high, so there's no evidence that is related. So an interesting question is, why is there only one repeating FRB? We now know of 23 of them. Some of them, not by any means not all, have been observed for quite a long time, tens of hours, maybe 100 hours in some cases, without any repetitions being seen. So could there be different classes of FRBs? Certainly a possibility. We can't exclude that. Some would have to be cataclysmic to occur only once, and obviously some not, like this object. But I do think it's interesting that the repeating FRB bursts are somewhat wider, and that's a little hard to quantify again because many of the Parkes FRB bursts are not well resolved by their frequency resolution given dispersion smearing. But also the spectra are more diverse in the repeating FRB than in the Parkes FRB population in general. So if FRBs in general had such varying spectra, you might think that the overall spectra that you saw as a population in the rest of the FRBs would show some of that variability, or would show some of that diversity, I should say, and they don't seem to. Of course, they're not necessarily selected for in that way. That could play a role, but again, we were also not looking for any particular spectrum. We were just combining all frequency channels with equal weights. But then again, is it a coincidence that of the 17, I should cross that out because those are the published ones, really 23 known, the only repeater is the only Arecibo FRB? Is that a coincidence? Well, maybe no, because in fact the repeat bursts are generally too faint to be able to see with Parkes. So it could be that every FRB is repeating, but just they're too faint to be detected with Parkes. What could the repeater be? I think it's fair to say we don't know. Different things that we've thought about a little bit, at least, are crab-like giant pulses or magnetar bursts, but I don't want to say too much about that because there's going to be a talk shortly on possible models. I will just point out that, for example, the crab pulsar is known to emit giant pulses. This is one particularly bright giant pulse that you could see the time scale here is microseconds. What's interesting is if you look in the frequency space, and of course this is at a much higher frequency than we're observing, 8, 9, 10 gigahertz, but you see these interesting ripples. You might think, well, if you're observing with a narrower bandwidth and you're just catching one of those ripples, that could explain something like what we see in the repeating FRB. That would also, you might expect there to be nanostructure in some of these repeating FRB pulses, as is seen in the crab giant pulse, some crab giant pulses. You might also wonder, could it be a magnetar? I'll just highlight some work that was recently done by McGill postdoc Sriharsh Tendulkar, where he considered the soft gamma repeater 1806-20, which had a giant flare back in 2004. This is the gamma ray light curve. It was one of the biggest, in terms of luminosity and probably flux, soft gamma repeater flare ever. And what he has done is gone to look, it so happened the Parkes radio telescope is actually observing a pulsar at the exact time of this flare, not pointing at the SGR, but because the SGR is galactic, you would expect any radio emission to be incredibly bright. And so he could set a limit on the ratio of the fluence in the radio band to the fluence in the gamma ray band. In this case, the ratio is constrained to be in this direction, and this is for different side lobe suppressions given how far off axis the SGR was. And the most typical one, the one that we think is the most reliable, somewhere around 70 dB. And that is very much the opposite of what is seen in all FRBs, for which no gamma ray emission has ever been seen. So the opposite is true of the known FRBs. This ratio of radio fluence to gamma ray fluence goes in this direction, and you see that it's just totally not in agreement with that from any of the FRBs. Okay, so just I want to mention now, how much time do I have?
7.
Okay. So now future surveys. Well, I'll just mention one survey that is ongoing that's, I think, has interesting preliminary results. We are in the process of surveying the northern sky with the Green Bank telescope. This is the Green Bank North Celestial Cap Survey. And this is a survey at 350 megahertz. PI is Scott Ransom. 100 megahertz of bandwidth, 2-minute dwells. We have been looking for pulsars, being very successful finding pulsars, rats, and we're, of course, looking for FRBs at the same time. We have a total of 26,000 beams that we've searched up to DM of 500, which is far greater than the maximum DM along most of the lines of sight in the GBNCC survey. 45,000 beams that we've searched up to DM of 3,000. And if you scale the nominal rates that Rane et al., for example, have estimated for FRBs, and you use a minus 1.5 spectral index, you expect a lot of FRBs. I put a tilde here. We're still working on exactly what that is, but certainly tens of FRBs to have been detected, whereas we've detected exactly 0 in this survey. This is work in preparation by McGill graduate student Pragya Chawla and others. That is perhaps a little distressing, but on the other hand, it's not hard to reconcile the rate that you would, that is implied if the spectral index is closer to flat, totally ignoring the possibility that scattering plays a major role, or even free absorption. So that's just an interesting, something that we're working on. I thought I should mention Utmost, a very interesting project. I know Vikram Ravi here is also working on this. This is using the Malangla radio telescope. You heard Sarah talk about this a little bit. 843 megahertz, 30 megahertz of bandwidth. This has already discovered 2 FRBs so far in 2016 with only 20% of the final sensitivity. At least that's the number that Matthew Bales gave me yesterday. And the localization capability is 10 arc seconds in the east-west direction, but 2 degrees in the north-south direction. So I think as this continues to come online, it'll be quite interesting. But now I want to talk about CHIME, which is a new radio telescope that is being built in Canada, a 100-meter radio telescope, a collaboration between McGill University, UBC, University of Toronto, and the Dominion Radio Astronomy Observatory. This is a unique design. You might not look at that and think it's a radio telescope. It's a unique design in that there are no moving parts. This is a software telescope, and let me explain. CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. It's located in Penticton, British Columbia at DRAO, and consists of these 4 20-meter by 100-meter cylinders, so there's a person for scale, acting as a transit telescope, so it can only view what's directly overhead. On each, and I should just say, to put it in Canadian terms, it's the area of 6 hockey rinks. So on each axis, there will be 256 dual polarization feeds for a total of 1024 feeds or 2048 input signals for the dual polarization, all sensitive in the range of 400 to 800 megahertz, so quite a wide bandwidth. The total field of view of the telescope is about 250 square degrees, so that's extremely large. I'll show you what the beam looks like. But this will be tiled thanks to a full correlation of all of these antennas so that we will end up with beam sizes that are somewhere between half a degree and a third of a degree. This whole project is funded by the Canada Foundation for Innovation. Let me just say a few words about how this works. If you had just a single feed on one antenna, this would be the beam pattern that you would see. The cylinder focuses in one axis only. If you then populate the cylinder with many of these antennas and do their correlation, you get these multiple beams on the sky. And then if you populate all full cylinders, you can go in the other direction as well, and you can end up with 1024 beams using all of the antennas. And so basically, it's like you have a GBT collecting area, but 1,000 of them, all looking at independent positions on the sky simultaneously. CHIME was originally designed for cosmology purposes. The goal continues to be to measure baryon acoustic oscillations mapping redshifted H1 to look for periodic fluctuations in the matter power spectrum. The bandwidth was chosen in order to get at a redshift range that's particularly sensitive to dark energy. And the CHIME Cosmology Collaboration, here you can see all the main players. You will not see my name in this list. I was not at all involved in the CHIME Cosmology project. The PI is Mark Halpern. This is the CHIME structure as of last summer, so the telescope is fully built, and this is the CHIME cosmology team standing in the axis. The antennas are being hung. The whole thing is being strung together this summer. The half-pipe array to map the teen universe, but that's not all. So CHIME can also be an excellent FRB detector. The fast radio bursts in CHIME, this CHIME's unique design, wide bandwidth, large collecting area, and enormous field of view can make it by far the most powerful FRB detector. This is a plot showing the number of bursts per hour versus with observing wavelength on the y-axis. You could see in terms of bursts per hour CHIME. Now, of course, exactly how you calculate these things. So I noticed on Sarah's plot, it's a little bit different from Longla. I think you could, the reason it's a large box, there's uncertainties in the population, but I think CHIME will be able to detect many FRBs per day. And in order to achieve this, using the original CHIME design, you had to redesign the correlator, which was not built originally, or not designed originally to spit out high cadence, high frequency resolution radio data like we need to search for FRBs. So we needed to redesign the CHIME correlator and add a dedicated FRB search backend. So we received a $5.6 million grant from the Canada Foundation for Innovation. And you might say, wow, how'd you convince the funding agency to enhance a telescope that doesn't yet exist? But that was not so hard. And it was also interesting to convince cosmologists that astronomy is interesting to do. But I think we're all now quite happy and very excited about this project, and we hope to be online by 2017. So the CHIME FRB collaboration, here's a small portion of us, the ones that were at this particular workshop. My collaborator, we have a project manager, Patrick Boyle, Ingrid Stair, Scott Ransom, Paul Demarest, a bunch of students, and the CHIME cosmology team. And so FRBs and CHIME, what would we want to solve this problem? What are FRBs? Well, you'd want statistics are going to help you. You'd love to have thousands of events so you can measure an event rate really well. Flux distribution, angular distribution, DM distribution, scattering versus DM, all of these things can test models for the distribution of matter in the universe. And of course, CHIME can deliver all that with the large event rates we expect. Study repetition rates. It's a transit telescope. We get those 1024 beams 24/7, every position on the sky. Anytime we detect an FRB, the next day we can look again for repetitions. So we will get all of the information about repeatings automatically for free using CHIME at the same time as the cosmology project is going on, and at the same time as we find new FRBs. We will have real-time triggers that we will make public as quickly as we possibly can. Arc-second localization with CHIME alone is not possible, but if there are optical or X-ray counterparts that are long-lived and bright, there are ways, especially with real-time triggers, we can hope to be able to localize some of these CHIME FRBs. Spectra and polarization, although the data that we search is full power data, so we don't have sensitivity to polarization as we do the search. For real-time triggers, we're hoping that we'll be able to dump baseband data and then do a reanalysis and extract things, better positions, better spectra, and polarization. And so, at last, stay tuned. We're very excited by CHIME, and I hope by this time next year we'll have some preliminary results. Thank you.
Questions?
There we go. So I reckon, are you going to be dumping the raw voltage data if you detect an FRB? Because if so, you should be able to get order of few arc-second localization.
Yeah, so for very bright sources, just from if a bright source lands in between multiple beams, then we can get localizations maybe to an arc minute or so. If you then are able to dump the baseband and reanalyze that, I'm not sure about a few arc second. I think that would be...
I reckon 10 for a signal to noise 100.
Okay, that'd be great, if you're right.
Yep.
I was just curious in this repeating burst, I mean, if it's at the cosmological distances implied by this excess dispersion measure, I mean, aren't the energetic constraints becoming just rather severe? I mean, I don't know how, the thing's been bursting every 3 hours for 3 years, right? It doesn't seem, so I guess I'm just wondering, I mean, I know you're not working on the models, but I just think that this, you know.
Right, so number one, at this XSDM, it doesn't have to be at a cosmological distance.
Right.
It could be at a gigaparsec or something like that. Okay, a few hundred megapart, well, I don't know. Yeah, right. But on the other hand, I mean, it's radio. It's not that much energy. It's not impossible.
Right, I just don't know, in like the giant crab flares, does the actual flare ever exceed the spin down power of the neutron star? I mean, if we assume that there's a neutron star
yeah,
there,
it's definitely many orders of magnitude brighter than any of the crab giant flares.
than the actual
absolutely.
spin down power, okay.
Well, I thought I'd just answer that. No, it's not. Look, you have Lorentz factors which are like 10 to the 8 here. The brightness temperature for this particular one will be like 10 to the 39 Kelvin. So these are like giant pulses. You have no idea what delta omega here is. And the real question you have to ask is, what is the radiation efficiency of this collective charge? And now, you know, we can go back to the pulsar stuff. So, pardon me? No. Yes, total energy. Yeah, that's fine. But at any given, so when you have, with this logic, when you see a giant pulse from a crab, it doesn't slow down. You don't see, you know. So the amount of energy that's radiated can be very, very small at any given time.
Beaming factor will always get you back here.
So,
by increasing the beaming, you'll always be able to reduce the overall energy expended.
yeah. So look, okay, I can make a gamma 10 to the 8. I can make it 10 to the minus 16. You know, in delta omega units.
But then the chance of heating up.
Absolutely. In fact, that takes the question you asked about the galactic plane. the suppression may be the opposite of what you're thinking, which is a point made by Jim Cordes, which is that, in fact, it is the scintillations which enhance the detection, which then get quenched in the galactic plane. So the suppression is in a very curious way, in which case the rates are amazing. They're not 10 to the 4 per day. They may be 10 to the 8 per day.
Actually, just one, well, just that one point about, Sarah mentioned the Marquardt and Johnston model, where there's this Eddington bias that you get more, you see them more often outside of the plane than in the plane. But I think actually our observations, not of the repeating, but just our improved constraints on the FRB rate in the Arecibo survey pretty much rule out that model, because in order to get that enhancement, they need a very, very steep luminosity or steep flux function. And when Arecibo has so much sensitivity, we don't see anywhere near the number of events that they predict we should see if their model's correct.